Swayam Prabha. Digital India. Educated India.
In this lecture, we will discuss modeling of a beam which has shape memory alloy wire attached to it for damping application. So, for that the problem that we discuss is taken from this paper by Gandhi and Chapui, passive damping augmentation of a vibrating beam using pseudo elastic shape memory alloy wires. Now, in this paper the material modeling that is used is based on complex elastic modulus. So, that is a different model. However, in our discussion we will use the constitutive relations of shape memory alloy that we discussed in the last lecture last week. So, and also many of our notations would be different from the paper. Now, the structure that is considered here is a beam and it looks like this. So, we have a beam structure, it is a cantilever beam and the beam. So, the cantilever beam has a externally applied load P and this load P can be time dependent, and let us assume that the load P is applied at a distance L B from the root of the beam and entire length of the beam is say L. And apart from that we have two shape memory alloy wires attached to it in this way. One is at the top surface here and another is at the bottom surface here, and they are symmetrically placed, which means the angle here and the angle here is same and both the alloys have same property. And let us say that the location at which the wires are fitted is at a distance L A from the root of the beam. So, at a distance L B we are applying the force, at a distance L A we are attaching the shape memory alloy wires for damping purpose. Now, here these two wires are pre-stressed, which means this length is more than the original length of the wire, which means under this undeformed condition both the wires are under some tension and the tension is equal because they are put symmetrically. So, if we look at the phase diagram of the shape memory alloy, which looks like this. Now, these wires are under pre-stress, tensile pre-stress. So, we may say that in the undeformed configuration it is somewhere here, and let us also assume that the material is under austenite condition in this pre-stress condition. So, it is in austenite condition. So, xi equal to 0 here, and because it is under some pre-stress we may say that in the phase diagram the material is somewhere here and here xi is equal to 0. So, when this beam tries to go up, so this point moves up. If the beam goes up, in that case the length of the upper wire reduces, which means the tension is reducing here. So, it generates some amount of compression because of the upward movement. So, the net tension reduces. That means, in the phase plane diagram, the upper wire goes down, the stress reduces, whereas the bottom part of the wire experiences increasing length because this point is going up. So, because of that the tension here it is under more tension. So, the beam further goes up, the bottom part for the top part of the top wire the stress reduces, for the bottom wire stress increases. So, when the bottom wire goes up and crosses this MS and MF lines, it becomes martensite, and then when the beam defaults in the downward direction, the reverse thing happens. So, the top part of it comes down, the bottom part of the wire which is here, it comes down and comes here. In that way, both the wires along this line, along this vertical line which is parallel to the sigma line, goes up and goes down. So, that means it shows some super elastic behavior, and we know that when the behavior is super elastic, it is associated with some energy dissipation, because a super elastic behavior looks like this. So, between the loading and unloading we see this loop, and that signifies dissipation of energy, and that is the source of damping generated due to the shape memory alloy wires. Now, here we have to keep one thing in mind, that depending on the amount of pre-stress these wires have and depending on the deformation this beam is showing, the wires can also cross this line and go to the compression region, that is also possible. If the compression is not very high, that is okay. If the compression is very high, then due to the compression also phase transformation may take place, and that we have to incorporate. However, if the compression is not so high, if the pre-stress and the beam deformation is such that it barely touches this line or just shoots little bit down, in that case we can we do not bother about the phase transformation due to compression, otherwise we have to take care of that into account. So, that is the entire mechanism of damping augmentation by this shape memory alloy wires. Now, we need to if we want to go to the mathematical model, we need to first see what are the forces acting on this beam. So, if this is our beam, it is fixed here, and we have seen that we have a shape memory alloy wire here and a wire here. So, we are just drawing the part which is attached to the beam. So, the top part has a tension T1 and the bottom part has a tension T2. Now, because they are symmetrically placed, when the beam is undeformed, T1 and T2 are same, otherwise T1 T2 are different, and we have a force applied P here, that is the externally applied force. So, because of the externally applied force, the beam vibrates, and the wire, because of its pseudo elastic nature, it tries to dampen the vibration. Now, if we draw the same diagram below, then these two forces T1 and T2, they give a horizontal force which we can call Fh bar, and they give a vertical force which we can call Fb bar, and apart from that there would be a moment that is induced, and that we can call as m bar. Again, if T1 and T2 are same in the undeformed configuration, the moment is 0, otherwise there can be a moment. And the force P that was acting here, that remains same. As per our consideration, this length is LA and this is LB. Now, we have to and also let us consider that the thickness of the beam is T b. Now, the question is what is f h bar, what is f b bar, and so on. So, f h bar if I consider this angle as theta or this and also this angle as theta in the undeformed configuration, then f h bar is minus of cosine theta and we have T 1 plus T 2 and then f v bar is T 1 sin theta minus T 2 sin theta and m bar is cosine theta T b by 2 multiplied by T 1 minus T 2. Because if I look at the horizontal component of the force T 1, it is T 1 cosine theta and also the horizontal component of force is T 2 cosine theta. So, T 1 cosine theta and T 2 cosine theta, if they are not equal, they are going to give rise to a moment which is of amount this, and P remains as it is. Now, considering all these forces that are applied, the variational form of the beam looks like this. The variational form is 0 to L rho A W double dot delta W, the variation of W, plus we have the internal virtual work which comes as W comma x x multiplied by W comma x x. Here W comma x x means derivative of W with respect to x done twice. And now comes the external virtual works due to these 4 forces. So, 2 forces F v 1, F v bar, F v 1, F v bar and F h bar and the moment m bar and also this force P. Now, the virtual work due to the force F h bar is 0 to integral of 0 integral within the domain 0 to L A of F h bar multiplied by W comma x into variation of W comma x. And then we have externally we have applied force F v bar. So, the virtual work here is F v bar multiplied by the displacement here. So, that is F v bar and the displacement at that point can be written as W at x equal to L A, and then we have moment m bar, and again we can write the displacement at because it is moment we have to multiply it by the virtual slope at that point. So, that is, so we have to put variation symbol here delta because it is a virtual displacement and here it will be virtual slope. So, delta of del W by del x at x equal to L A, and then we have externally applied force P. So, it is P multiplied by W at x equal to L B. So, this is the total virtual work equation for this problem. Now, the question is why this expression is so, why is the virtual work done by F h bar looks like this. So, at this point the force F h bar is applied and it is applied horizontally. Now, the virtual work done by this force is this force multiplied by the virtual displacement at this point. Now, we are assuming that the beam is extensionally stiff. So, there is no extension or contraction in this direction. However, because the beam bends and because of the deflection in the vertical direction. So, if the beam the part of the beam from x equal to 0 to x equal to L A in the undeformed configuration was like this, then because of the deflection it deforms in this fashion. Now, the length of the neutral axis remains same. So, this part this length is same as this length, which means that there should be some difference in x coordinate of this point from this point to keep the length same, because this is a curve and this is a straight line, and this displacement is half into w comma x square 0 to L A dx. So, the virtual work done by that force is F h bar multiplied by half into variation of w comma x square integrated from 0 to L A, and then we know by the property of this operator that this is equal to twice w comma x multiplied by variation of w comma x. So, finally, the expression becomes w comma w, finally, the expression becomes w comma x multiplied by variation of w comma x dx. So, that is here. Now, f h is this. So, once we take this negative sign inside, this entire expression becomes positive. So, f h is a negative quantity, that is why it works in this direction. So, this is the virtual work expression for this. Next is we have to do the finite element formulation. So, if we discretize this entire beam into a set of elements, it looks like this. So, we can call it element number 1, and there is a generic element, maybe element number E, and then let us call an element number n. So, at the second node of element number n, say we have the shape memory alloys wires attached. So, here the forces due to the shape memory alloy wire is experienced. So, I have F b bar here, I have F h bar acting here, and I have the moment m bar acting here, and let us say we have element number m, and at the end of the element number m we have a force P externally applied force P acting here. So, while discretizing we have to make sure that the point at which the loads are applied, these point loads are applied, they lie on some node. So, for this case the first point where I have the shape memory alloy forces acting, that is at the second node of the nth element, and the point at which the force P is acting, that is at the second node of mth element. Now, we have to do the finite element formulation. So, after doing the formulation as described in last 2 lectures, the elemental equation that is obtained is m e multiplied by d e plus the elemental stiffness vector multiplied by d equal to 0. So, in this case we do not have any distributed force. So, we are keeping the force vector 0. There are some discrete forces that will apply later on after assembling all the equations. Now, as we saw before, the m I j has the same definition, rho A multiplied by NIE NJE dx. So, each element has a local coordinate system going from x equal to 0 to x equal to LE, where LE is the length of the element. We can draw it here once more. And K has two parts, because if we look at the virtual work equation here, K comes from this equation as well as this equation. So, finally, K has two parts, we can call it K 1 E plus K 2 E. K 1 E has contribution from this expression and K 2 E has contribution from this expression. We know what is the contribution from this expression, we discussed it in last two lectures. So, K 1 E I j is as seen before E I n comma x x n I comma x x and n j comma x x dx, and K 2 I j is negative of f h bar multiplied by 0 to L E into n I comma x multiplied by n j comma x. So, if you follow the same procedure that was described while discussing finite element method in last two classes, from this expression we get this as a matrix. Now, this quantity is valid only between x equal to 0 to L A, because this integral is from x equal to 0 to L A. Beyond x equal to L A, this quantity is 0. So, we can maybe define a quantity here eta, which is multiplied here, and we can say that eta equal to 1 when E is less than equal to n. That means, any element where the element number is less than equal to n, which means any element which lies between x equal to 0 to L A have eta equal to 1. That means, this quantity is as defined, otherwise eta equal to 0 when E is greater than n. So, anything beyond the element number n, those elements do not have any contribution from K 2, and the force matrix is 0 for the time being. And then after we assemble it, after assembling, the entire system looks like this. So, after assembling, this is our globally assembled matrix. The assembling process we discussed in the last two lectures. So, this is my global mass matrix and this is my global stiffness matrix. Mass matrix is multiplied with the global degrees of freedom, the second order derivatives of the global degrees of freedom, and the stiffness matrix is multiplied with these d's. And then what we do here is we apply the essential boundary condition. So, as per the essential boundary condition, the beam is fixed at the root, which means the first two degrees of freedom d 1 and d 2 is 0, because we know that d 1 means our d 1 means displacement at the first point and d 2 means slope at the first point. So, they are 0. So, we can just strike out these corresponding rows and columns, and whatever is remaining is our reduced set of equations, by solving which we can get the solution. Now, here we have a globally assembled force matrix, and this force matrix we are calling F, Now, this force matrix is not entirely 0, because we have to incorporate the contributions from the point loads that are applied here. So, how did it come? To discuss that, let us first look at the numbering of the global degrees of freedom. So, we have D1, D2. So, D1 is displacement at the first node, D2 is the displacement at the second slope at the first node, and then D3, D4, it goes on. Here the degrees of freedom becomes D2n plus 1 and D2n plus 2. Similarly, at the end of the mth element, it becomes D2m plus 1, D2m plus 2. Now, the effect of FH is already incorporated, because my K2 matrix has FH here. I need to incorporate F V bar. F V bar is the vertically applied force here. So, that corresponds to the degree of freedom D2n plus 1, because D2n plus 1 is the displacement. So, force in the virtual work equation, force is multiplied with the virtual displacement. Here the displacement is d of 2Tn plus 1. So, F V bar corresponds to the degree of freedom d 2Tn plus 1. Similarly, this is moment, and moment is multiplied by the virtual slope, and the slope is here d 2n plus 2. So, m bar is multiplied with the variation of d 2n plus 2, and here I have force here. So, that corresponds to d 2m plus 1. So, accordingly, in the force matrix we have to put the definition of the force matrix goes like this: if I equal to 0, if I is not equal to 2n plus 1 and I is not equal to 2n plus 2 and also I is not equal to 2m plus 1. So, other than 2n plus 1, 2n plus 2 and 2m plus n, 2m plus 1, for all other indices f I is 0, and f I at 2n plus 1, which we can write as f of f 2n plus 1, is the vertically applied force, because we have seen that the vertically applied that vertical force due to those shape memory alloy wires corresponds to the degree of freedom d 2n plus 1, and f 2n plus 2 is accordingly m bar, and f 2m plus 1 is accordingly p. So, these three, the force matrix for these three indices have some values, otherwise they are 0. So, here it is not that everything is 0, these three quantities are non-zero, rest of them are 0. Now, after we strike out everything, we are left with rest of the system, and we solve rest of it and we get our solution. So, the rest of the system, the global FE equation, global finite element equation after applying essential boundary condition let us write as m d double dot plus k global k d equal to f. So, if we solve this equation, we will get our d, but here again we have to understand few things, that the components of the force vector, if we go back, which are f bar, m bar and p, and also in the K2 matrix we have f h bar, they okay, not the P is the externally applied loads. So, the other components F bar and M bar and this F h, they come from the contribution due to the shape memory alloy, and the shape memory alloy wires have stresses, and those stress are dependent on the strain in the shape memory alloy wire, and those strain depend on the displacement at this point. So, the force F bar, moment M bar and this force F h bar, they are function of the displacement at that point itself. So, here force is dependent on the displacement. So, based on the force we can solve and get the displacement, but again the displacement influence the force. So, it is a highly nonlinear problem, and that needs to be solved by iteration, and that we will discuss in the next class. Thank you.